what is this ADC? And to start talking about these analog inputs and analog outputs, I like starting out with the DAC, the digital to analog. So we are in a computer. Everything in a computer is stored binary, ones and zeros, right? Our integer values, even our floating point numbers, is a bunch of ones and zeros, right? We want to get a voltage out to the world. Well, this DAC, digital to analog, can do that for us. There's all sorts of different DACs out there. The common ones are 12-bit to 16-bit, used a lot. There's probably some 20-bit, higher bit DACs out there, not used as much, but if you need a really precise output, they do create those for you. 12-bit is usually, depending on your range of voltage, but it's used a lot just because of the electrical noise that's out there, the radio interference that's coming in on your board and in different places. You can't get much better resolution. Now, if you're oversampling and averaging and all that kind of stuff, that's where you can get rid of some of that noise, but it's always a challenge. So most microcontrollers have 12-bit ADCs, and some have 10-bit even less resolution. Okay, this one has its DAC can only be 12-bit. Its ADC can actually be, the ADCs we're talking about can actually be set up to be 16-bit. If that sounds something you'd like to play with in your final project, please tell me. I've not played with that option on these ADCs. I've never set the 16-bit option. It'd be interesting to see if we can get a little better sampling, less noise and things like that with it. So let's start with the DAC. The idea of 12-bit DAC means a number between 0 and 4095, in the case of our microcontroller, needs to produce a voltage between 0 and 3 volts. And we talked about that a little bit at the end of last lecture, that if we've got this range 0 to 4095, we map that linearly to a DAC. So 0, this integer, 0 to 4095, we map that to a voltage starting at 0 volts up to 3.0 volts. Okay? That's the range we can output with this digital to analog converter. There's other DACs out there. I use, and some of my stuff I use in the labs over in ECE for other classes, my DACs over there range from minus 10 volts to 10 volts. So you can get different voltage ranges. Really all it is a bunch of op-amp circuits inside all that. How much do you guys remember about op-amps? So the DAC actually is an op-amp circuit. So let's think about it a little bit. So this number from 0 to 4095 is a 12-bit number. Bit 0, bit 1, bit 2, bit 3, all the way up to bit 11. Okay? So we've got all these bits. All right. Well, what is a DAC? A DAC is going to take these ones and zeros and output a certain voltage. So if you remember from your op-amp days, if you had a little bit of op-amp days, we've got negative feedback, minus, plus. This is what's called a summing op-amp circuit. So we ground, and there's all sorts of circuits, but this is the standard one. We ground the positive input, and then with negative feedback, just some resistance, R feedback or whatever. Now all these resistance are very important, but we're just going to draw them as a resistance. And then to some different voltages, you put a resistance here, and you got voltage. Let's call it voltage 11 for just a second, because we're going to have through 0. Yeah, that's fine. And then another resistor, R2, voltage 10, R3, voltage 9. We keep on going. R4, voltage 8, all the way down, boom, 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 kind of all the way down to voltage. Let's do a couple down here. Voltage 0. So this would be resistance 12. Kind of labeling this kind of weird. Voltage 0, and then resistance 11. Voltage 1. I'll do one more. We got in between voltage 2. Sorry, not 3. All right. So this is for the 12-bit, and then, as I said, dot, dot, dot in between here. So what happens here, think about it. Well, and you know, one other thing, sorry, I should have drawn this too. With all these voltages can be turned on and off. So voltage 0 really has a switch here, okay, that you can turn voltage 0, you can connect it to that resistor or not. Voltage 1. See what I'm doing here? Kind of. All right. So we have control over those switches, and they're really transistors, right, inside this. And we can apply that voltage to this circuit, or we can not apply that voltage to this circuit. And that's true for all 12 of these voltages. Okay? Now, to get this thing linear, and maybe we should just talk in terms of a 4-bit DAC first. So let's just imagine we have voltage 0, 1, 2, and 3, or whatever. Okay? So what if we did this? We have these 4 bits. Okay? And so we call this bit 0, bit 1, bit 2, bit 3. So if it's all zeros, we want to be outputting, right now we're not thinking about negative voltage, we want to output 0 volts. Agreed? Okay? So what we would do is we would turn off all these switches. None of these would be on. So 0 volts would be coming into this op amp. We would sum no voltages. Okay? And so it'd be 0. Now, what if we do set bit 0 to 1? Well, when it's 1, we want to be outputting the minimum resolution of the DAC. Okay? For our 12-bit DAC, that would be 1 divided by 4095 times 3 volts. Agree with that? We said last time that's about what? 0.73 millivolts or something like that, whatever it was. Right? Really small number, whatever it was. We should probably do it. What's 3 divided by 4095? Calc. 3 divided by 4095 equals, 0.73 millivolts. Okay, so in that case, that's for a 12-bit. So in other words, right here, the voltage sitting right here at V0 is 3 volts divided by 4095. In a 4-bit DAC, right, this voltage V0 would be equal to 1 divided by 16. 3.0 divided by 16. That's not much of a DAC, is it? If you have an analog voltage output that's only got, and that should be probably divided by 15, but anyway, that just has, 16 different voltages you can output. That's not much of an analog voltage, is it? So, there's no such thing as a 4-bit DAC. But the idea is, at voltage 0, you would have this divided by 16. At voltage 1, you would have 2 times this. At voltage 2, you would have 4 times that, and then 8 times. So do you see what I'm getting? Let's think about this. So our voltages, right, V0 coming in with a 4-bit would equal, and let's just do 3 divided by 15. Okay, what is that? Let's get that real quick. So 3 divided by 15. I should know that, right? Is that easy? 3 divided by 15. Is that 1/5? What am I? My brain's not. Yeah, it's 1/5. All right, 0.2. Okay, and now if we again had this 4-bit DAC, what if we then V1 would equal 0.4, V2 would equal, let's see if I'm doing this right, 2 times that, 0.8, and then V3 would equal 1.6. Okay, and remember, we're taking these voltages and we're going to summer. So forget the op-amp circuit for a second. Let's just think of it, I mean it's a summing voltages, but we can also think of this as a summer giving us our DAC output. Okay, and so you got voltage 0 with a switch, you got voltage 1 with a switch, you got voltage 2 with a switch, and voltage 3 for our example 4-bit DAC. All right, now let's think about what voltage is output. What is our maximum voltage we can output, right? Our minimum is 0, of course, is our minimum. But if we just turn on one of these bits, this guy on, we'll get out 0.2 volts. Agree with that? If we set all the bits to 1, 1, 1, 1, 1, then we get 1.6 plus 0.8 plus 0.4 plus 0.2. Agree with that? So that gives us what? 2.4, 2.8, 3 volts. Did I add that right? 2.4, 2.8, yeah. 0.2 is 3.0 volts. You see the range there? And by turning these switches on and off, I can get 16 different voltages between 0 and 3 volts. And this number right here is just your DAC value, the raw binary value between 0 and 15 that you can send to this DAC. What do you think about that? Am I making that clear there? So that's all this guy is up here. Now we just have to do it with 12 switches, right? A 12-bit number. And again, if we add all these up, these are all on. This would be times 2. So this would be 6 divided by, let me think. Yes. This would be times 2, times 4 of this resolution, times 8 of this resolution, and so on, the different voltages. Agree with that? Okay. And those, and now the key, the hard part, this is an op-amp. Technically, we could just patch this up with an op-amp on a breadboard. Okay? Now it takes some doing. All these resistances right here have to be really precise, because what's happening here is actually it's the same voltage coming into each of these ports, but the gain is this R4 and the feedback resistor creates a gain less than 1 that multiplies by 3 volts to get us that fraction of the voltage. So what they do when they design these DACs, they have to laser trim the resistors. I don't know what that exactly means, but they have to get in there and just make these resistors super precise. It's called, if you ever search for what's called an R2R ladder DAC, that's what this thing is. You check that out. But anyway, that's the key to making these DACs. To make them linear is to really fine tune those resistances so they're exactly, as close as you can, correct. And then it's a very nice linear output from this op-amp circuit to give you this digital to analog converter. Okay. Good. All right, so that's this idea of a DAC. And we'll be using it this week in lab. You'll be writing values to the DAC unit. Actually, let's see. Yeah, and I think we give you the function, but either way, you'll see how it's done. You'll take the value between that you want to output, say 2.1 volts, right? And you'll go to a conversion of converting that to the linear representation between 0 and 4095, whatever scales to 2.1 volts, right? Okay, so you'll be driving that to the DAC, and then the DAC will output that voltage. Okay, good. Now, the opposite end is bringing in the analog value. So now we're going to have a sine wave. We're going to use our function generator in lab, and we're going to create a sine wave of voltage, maybe from starting out let's say it goes 0 to 3 volts. We'll do it a little lower range than that. We'll probably go like down at start at 0.25 volts, go up to 2.75 volts, and we'll make a sine wave that does that. So it's in our range of 0 to 3 volts. Okay, so that's our signal that we want to bring in. So every millisecond, initially every millisecond, we're going to want to go read the voltage that's sitting on our pin. Right? Just the same with the DAC, this output goes to a certain pin on our processor, the 28379D, and then goes out to the world. Right? And we can scope it, that DAC out. In the same way, there's a pin on our 28379D processor, many pins actually, that can bring in voltage, can what we call sample the signal, or read what voltage, figure out what voltage is coming in on that pin. So that's where we have to go next. Neat thing about the DAC and some of our other sensors or outputs, PWM too, is you just write to the DAC that integer value, and almost instantaneously that voltage is output on that pin. It's not instantaneous. All op amps, if you know much about them, have a slew rate and all this kind of stuff. So there's a little bit of time constant from when you set the DAC to a voltage and it outputs that voltage, but it's very quick. Okay? Orders of nanoseconds. ADC is a little different. That's why we got to get this concept in our head a little bit better for the ADC. You can think of the ADC having to go through a search algorithm to figure out what voltage is on the pin. Okay, and I'm getting to that. Yes?
So then does that mean any combination of these voltages, there's no one combination that's the same as another combination?
Correct.
It's like linear independent?
That's right. It's a scale, 0 to 4095. All those map linearly to 0 to 3 volts. Yep, because all these voltages are different. None of these are the same. This is the smallest voltage. This is 2 times voltage 0. This is 4 times voltage 0. 8 times voltage 0. Okay, good. Okay, now, just to get you thinking too, a lot of you, I tested out your optical encoders. Remember those sensors that are on your wheels? We saw that they were working and all that. Well, for example, to read that, let's see if I left it here in my co-composer. Let's see. I don't have it. Okay. Anyway, there's the optical encoder. It produces. We're going to talk a lot more about the optical encoder, but it produces a bunch of square waves. Actually, 2 square waves that are 90 degrees out of phase of each other. And the idea of this quadrature coding, decoding, counting is all done inside the CPU in what's called the EQEP. The only reason I'm talking about this is it's one sensor that whenever the processor wants to know what count the quadrature encoder is at, it can read it immediately. There's just one register that's keeping track of this count, and this count is proportional to radians that the wheel is spun. All right? So counts relate to angle. And whenever you want to, the processor can just go boop, read that register, and now you know the angle of the wheel. Again, so that's a very nice sensor. Kind of everything's happening in the background. The ADC is different. We have to tell it to convert, and then we have to wait for it to be done, and then we go read it. Okay? So that's what this concept I'm trying to get us to think about. So let's just to get you understanding that a little bit, let's go through another block diagram or a little circuit for the ADC. Come back to me. There you are. All right. So we have this unit, and there's actually 4 of these units. There's ADC A, ADC-B, ADC-C, and ADC-D inside our processor. Okay? Why do we have multiple ones? Because sometimes, especially with motor driving, you want to know the current of the phases of your three-phase motor control. Not with our DC brush style motors, but with these brushless style motors. It's very nice to be able to know exactly at the same time what current is going through those coils. And so they set up multiple ADCs so you can sample those all exactly at the same time. But for our lab, initially we're going to focus only on ADC channel or ADC unit D. Then after we figured out D, we are going to use B and A, but you'll see that, what we do with that. Okay, so we've got this unit inside the 28379D, and it's called ADC-D. Now, just as this picture shows here, we've got multiple pins that come into it. Now, where are we at? Let's go to my PDFs. Right here. So if you go down this nice little colored picture, here's our ADC-D, and these are the pins that actually come into the unit. Technically, it's set up so that it can read 16 different channels, different pins of the processor. But for this device, the 28379D, they have chosen for some reason to only give us 6 pins and possible 2 other ones. Let's see, yeah, those are called, and I've never used these either. For some reason, they bring the same pin into all the ADCs, and they're called, where? Is that A0? No. It sure is. Yeah, for some reason, look at A0, ADCN A0 goes into pin 0 of the ADCA, plus it goes into pin 12. I don't know. There must be some method to their madness. It also goes into ADCB pins 12. And then also there's these other pins called, again, we're not going to be using these. Where are they at? Yeah, it's just called ADCN 1415. Notice how these are called ADCN A1. So in other words, these pins are just for ADCA, except for this silly A0. But then this 1415 are for all the ADCs. Great question why they have those. I don't know if they did that for calibration reasons. I'm not sure exactly, but they've chosen that. The other thing to know, and again, really not important to us, but putting ADCs on a high-speed microcontroller is actually very difficult on the analog end of things. It not getting mixed in with all the noise of the processor, all these, processors, what are they doing? Bits are going high, low, all the time. Clocks are going up and down, all the way up to 3.3 volts, back down to 0, right? That causes bouncing of ground, that causes noise. And so when companies do this, they always have to do some tricks, I'm sure, to get these ADCs working well. I'm sure they've gotten those tricks figured out more and more as years have gone by. But still, I bet that's some reasons why they don't give you all the I/O pins. So in other words, they're leaving this up for future processors. Maybe in future processors there will be something connected to channel 6 and 7 and 10 and 11 or whatever. Okay? But these happen to be the ones. Then in addition, not only do they limit the pins in their actual design, the launch pad itself limits pins. And so if we go to the PinMux guide, I show you, down here at the bottom of our PinMux guide are all the analog input pins that we have to work with. And there's a few missing. I always forget which ones exactly are missing. I think there's A1. But anyway, you can look through this, and some of the ones on that diagram I just showed you are not brought out to our pins on the red board. Right? So these are the pins we have on the red board. We also have a separate header that doesn't come out to the 80 pins. There's a separate header called J21. Actually, that's where we're going to get ADC inputs D0, D1, D2, and D3. We'll show you where that is on the board during lab. Anyway, that's where we're going to get our ADCD input pins. And so, back to my drawing, all that explanation there, back to my drawing of the ADC. Where did it go? Right there. All right, so let's just think about then those 4 for now, but the mux could be larger than this. So we've got this, what you would call like a multiplexer, that determines if ADC in D0 or ADC in D1 or ADC in D2 or ADC in D3. Oops, that's a B down. D3. Ah, did it again. Come on. D3. I'm thinking of a D and a 3 together, making a B. All right. So those are the 4 pins out there that could, and then again, there's a few more, but we're going to think about those. Those 4 pins could come into the ADC and get sampled. Only one of those pins' voltages can come in at a time. So you're going to see that the ADC has a sequencer. And we can tell ADC D0 to sample first, then D1, then D2, then D3. And we'll talk all about that. But for now, just think about, okay, so we got some voltage coming in. You know, it's a sine wave, moving voltage, or it could be, like you're going to use in lab, we're going to give you a little potentiometer joystick. And as you move that joystick, you know, a different voltage is coming into the ADC pin. Or we're also going to use in lab, not on these D pins, but on our, I think it's B, we're going to bring in our microphone signal, right? And so when we whistle, there's a sine wave. Or when we're just talking, it's all the, you know, the crazy looking voltage changes, right? When you talk, you've seen that on an oscilloscope before, or in a movie, right? Where you see your voice going across. Anyway, so that those can get sequenced into the ADC. All right. And you kind of think of this input here having a buffer too, and they kind of call this little unit the sample and hold. And there's a switch right here from the signal coming in into the sample and hold unit. Okay? And then the internals of this ADC. There is actually, now there's no way for this to come out to the world. It's just internal. But there is a DAC inside this, a 12-bit DAC. Just like the DAC I just showed you, that can create a voltage between 0 and 3 volts. Okay? And so then there's kind of this, you know, the ADC value register, ADC value. And yeah, it's got 12 bits again. So we got, well, we'll draw it over here. Here's bit 0, bit 1, bit 2, 3, 4, 5, 6, 7, 8, 9, 10, bit 11, right? So there's all those, boom, 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 all the way over here to bit 11. So our job, the job of this ADC is to figure out what ones and zeros get to the closest voltage that's coming in on this pin. And again, this voltage needs to be in the range of 0 to 3 volts. If it's higher than 3 volts, like say it's like 3.3, this guy will just read 3 volts. It saturates a little bit. But obviously, if you bring too big of a voltage into that ADC port, it'll damage the ADC. Okay, but you can bring a little bit higher voltage into this ADC, and they'll just see it as 3. You can go a little negative too, and it would go 0, but a big negative would also damage this ADC. So we're assuming these voltages are between 0 and 3. And we actually, on our board, we have a protection chip that doesn't allow it to get greater than, well, I guess that protection chip is not allowing it to get greater than 3.3 volts, but either way, that's good. Nothing can damage if we use that protection chip. And we'll use little jumper wires to jumper to that and all that kind of stuff in the lab. Okay, so we need the ADC, every time you tell it sample that voltage, it needs to figure out what ones and zeros go here. Okay, so it's kind of neat what this does. So think about this. There's a comparator inside here. So we've got this comparator. And it just says if the DAC voltage is higher or lower than the input voltage. So I'm going to draw this like this. So here's our input voltage. My goodness. Here's our input voltage coming into the comparator. And this little comparator just says, is it high? Is DAC higher? I guess is a good way to say it, in voltage. And see, this DAC voltage comes in here. All right. So let's do an example. Let's say we've got 1.5. Nah, that's too easy. Not 1.5, Dan. Come on. Let's say we've got 1.1 volts coming into ADC in D0. This is a pin. So there's 1.1 volts sitting on this pin of the red board. Okay. That we tell that to sample. Okay. What happens then is this switch, so for the whole time until we say it's sample, this switch is actually closed. When we tell it to sample, this switch opens up and the sample and hold holds the voltage at 1.1 volts. That's why we call that a sample and hold. So you tell it to sample, the voltage had been going into the sample and hold and changing with the sine wave. But then when you tell it to sample, that opens up so that our signal can't mess with it while it's doing its sample routine. Okay? Because it takes a little bit of time. Not a lot of time, but a little bit of time. Okay, so we sample and hold, and then we start converting. Well, what do? We set first bit 11 to 1. Well, remember bit 11 on our DAC is actually half the voltage. So that would be the same as setting DAC equal to 1.5 volts. You agree with that? Or if you want to get really technical, it's what? It's 3.0 times 2048 divided by 4095, right? Really close to half the voltage, right? Half the VCC, half of 3 volts. Okay. So we've got 1.5 volts coming out of the DAC, and we've got 1.1 volt coming in here on the input. So this comparator looks into that. It says, is DAC higher? Yes, DAC is higher. So it knows that truth. There's a little, there's a little bit of computer logic inside here, maybe a little bit of a processor checking these things out or whatever it needs, and it sees that it is higher. So it knows not to set that bit. Do you agree with that? 1.5 volts is not in that signal of all ours, right? Because this is going to output 1.5 if we set it. This is going to add 0.75 if we set bit 10. This is going to add 375? Help me out. What's half of 0.75? 3.625? What is it? What's 0.75 divided by 2? 375, thank you. Brain's not working. And then, of course, 375 divided by 2, right, is bit 8. See what I'm doing? Okay, whatever. What's 0.375 divided by 2? Whatever that is, right? And so on. It's just a half as we march down. Okay? So we find that 1.5 is not in our signal, so we set that bit to 0, or the ADC does. Then it sets this bit. That makes 0.75 come out of the DAC. Agree with that? Because it's 0. All these other ones are 0 right now. Only 1, 1. So 0.75 is, DAC is not higher now. Okay? So it sets that, leaves that bit set. Then it'll go and set the next bit and add 0.75 and 0.375. It'll find that that new voltage is higher than 1.1 volts, I believe, right? just barely. And so this one will be set to 0. See what I'm doing? And it just marches along. I believe this one will be set, won't it? I think when we add those up, that would be less than 1.1, won't it? And so on. It just marches down through the bits and finds what all those bits need to be by just comparing that voltage to comparing the input voltage to this DAC voltage that's changing as we're figuring out what voltage is coming in. What do you think of that? Yeah, pretty neat technique. And do you see how it's kind of a search algorithm? Now, it's a deterministic search algorithm because it, just does one bit at a time, boom, 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 through there. But it takes some time to figure this out. You can't just do this instantaneously, right? There's op amps, comparators, there's all these rise times, slew rates, and all this kind of stuff in your analog circuit. So you can't just immediately set it to 1 and then check. There's set it to 1, wait a little bit, and then check if that is, see what the comparator says. So there's a little bit of timing that's going on inside there. I've played around with this ADC, and I found it to work pretty darn well, being faster or as fast as 500 nanoseconds. So that's pretty darn fast. But remember, an instruction on our CPU happens every 5 nanoseconds, doesn't it? So you can't just say ADC convert and then go read its value the next instruction. Okay? We have to say convert, and then what are we going to wait for to know that its conversion's done? What do you guys think? Yeah. Okay, so you could do that. We tell it to convert, and we could sit then in a while loop checking the status of the ADC. Usually in an ADC there's what's called a busy bit. Is the ADC busy? So we could sit there in our timer. Let's say our timer happens every millisecond. And we tell this ADC to convert. Well, we sit there and we tell it to convert, and then we sit and wait. We check. Is the busy bit still set? Oh, it is. Okay, continue. Check again. Check again. Check again. So we're sitting in a while loop waiting for that to be done. Okay? Well, we're going to sit there for 500 nanoseconds. Well, that's not too long, you think. But what if now remember, we're going to make a sequence. We're going to tell it to convert D0, D1, D2, D3. So that multiplies this by 4. So now you're waiting 2 microseconds. Again, that doesn't sound like a long time, but it is when you think about all the processing that could be done on the CPU during that time. So sitting there in a while loop waiting for the busy bit to go low. No, I'm not busy. Okay, go read the values. Is a waste of the processor time. So instead, what we're going to do is we're going to tell the ADC to convert, and we're going to wait for the ADC interrupt. And we're going to have an interrupt function be called when the ADC is done. Okay? Just like our timer interrupts. That makes some sense? Okay. And actually, what we're going to do in lab, and let's see, yeah, I'll get to that more next time. Let's just continue here. But we're going to have a PWM channel tell the ADC when to start. You can actually have the CPU timers do it also. You could have the CPU timers be a trigger for this ADC unit to tell it to convert. Because what we always, with these ADCs, we want to sample at a certain rate. Microphone, the faster you can sample, up to like, a lot of times they sample microphones, and for good audio is like 44 kilohertz. So very fast. I can't remember what we're going to do some rate like that. We don't go quite as fast as 44 kilohertz. We just really don't need to for what we're going to be doing in lab at least. But we are going to sample that at a pretty fast rate. So we can set up these timers, set up this PWM to tell it to sample at whatever rate. When it's done, it will generate an interrupt, and then in that interrupt code is where we'll go read the result of these samples. Okay? So in other words, giving the processor all the capabilities, letting it do things while the ADC conversion is going on. That's the whole point of the interrupt. And all we do in the interrupt is we get in there when we know the ADC sample, we'll go read the results, convert those results to a float that is a voltage value, and then do something with that. Do a filter or whatever. Yeah.
What happens if the input signal is changing? How does it decide what part of the thing to convert to?
Okay. So remember what I said is, so we're going to set up EPWM5 to time out every, I think initially we tell it to time out every 1 millisecond. Okay? So at that moment of time, at 1 millisecond, and I kind of drew this a little wrong, each of these have their own sample and hold. You can think of that. Okay? And at that time, boom, that switch opens up. And those guys are sitting, their voltage is sitting in that sample and hold arena. Is that true? Let me think about that. I take that back. No, I think there is just one sample and hold. But anyway, so the idea is when you tell it to sample, this switch opens. It doesn't close, the switch opens, and the voltage is held inside this sample and hold unit. It can hold it here long enough for the ADC to do the conversion. Does that answer your question? Okay, good. So yes, that you don't want the voltage changing while the conversion's going on. That's why they have a sample and hold unit. Yeah.
Then the DAC inside the ADCD, why'd you pick 1.5 volts? Is that something that is like preset, or is it?
Yes, and it's just like the DAC I was talking about before, those different voltages. Remember, they're all summed up. This is the highest voltage. When that bit's set and all these other ones are 0, it's going to output 1.5 volts. And our DAC that goes out to the world does the exact same thing. It's half your range. This is half your range, this is fourth your range, this is an eighth of your range, this is a 16th of your range. And when they're all ones, add them all up. It's the full range. Right? When they're all ones, 1, 1, 1, 1, 1, 1, then you got 3 volts. Okay? Good. All right, anyway, so the main gist of this is, it's good to know what's going on inside, but the main gist of this is for you to know, when you tell it to sample, you can't go read it right away. The only place I'm going to allow you in this class, at least for the labs, to read the ADC results registers is inside the ADC-D interrupt service routine, ISR. Technically, and that's what always gets people, and this is, I call this Arduino programming. But technically, you could just go, you could tell it to sample, and you could go read the results register immediately. The issue is, what's sitting in the results register? It's the value you told to sample 1 millisecond ago. Okay? You're getting a 1 millisecond old value, and in most cases, that's not a big deal. In my class, that is a big deal. We want the most current sample. Okay? So, we tell it to sample, we go off, do other things. Or we have the PWM telling it when to sample, however we're doing it. But then we know things are done when the ADC interrupt is called, and then we read the results registers inside there. Okay. So, anyway, we've got 3 minutes. Tomorrow, on Wednesday, we'll talk about the sequencer. And there are these units. So this ADC's got a bunch of complexity to it. They make it, almost too complex in the sense that you could tell ADC channel 1 to D1 to convert, then D3, then D6, or whatever. You could do it all these different orders. And I guess if you if you kind of were a little lackadaisical in where you route your signals on your board, maybe you'd want to sample in a weird order. But it makes so much more sense just to sample pin ADC in D0, then D1, then D2, then D3. So your code doesn't get confusing. But the sequencer allows you to do it in whatever order you want. So what they have, and we'll get to it, we've got to get some labeling going on too. We have ADC, A, B, C, and D. Those are the ADC units. And each of those units have ADC in A0, in A1, in A2. Those are the pins. So this is the unit. These are the pins. Then there's another labeling. There's the interrupts. There's ADC, A1, A2, A3, A4. There's 4 possible interrupts. We're only going to use the D1, A1, C1, whatever. We're only going to be using the first interrupt source. But, so they make this super complex so you can do some crazy things. Anyway, finally, in each of these ADCs, there's things called start of conversions, SOC. And there's SOC 0 through SOC 15. And this is what I got to talk about first thing next time. You associate with a start of conversion a pin. And this is what tells the sequencer, okay, sample this pin first. SOC 0 is always going to be, for us, is always going to be the thing that samples first. Then SOC 1, then SOC start of conversion 2, then 3. And then it goes back to 0 and does it again whenever you're ready to do it again. But again, there are ways to rearrange those SOCs and everything like that. We're not going to get super complex. But anyway, and then the SOC, there is results register 1, results register 2, 3, 4. And the results registers are associated with the SOCs. So I got to explain that some more next time.